Hello students. Now in this video I will be solving the problem on a convolution integral. Here the signals that we have considered are different type. One is a rectangular one and another one is a exponential signal, decaying exponential, which is varying from 0 to 1 only, and this exponential signal is defined by 4 into e to the power of minus t. Since 4 into e to the power of minus t, it is decaying, and 4 is the amplitude at origin, and it comes to 0 after 1. So the signal exists from 0 to 1 here. Now this is x of t, and another one is h of t. We can perform convolution in both the method, that is x of t convolved with h of t or h of t convolved with x of t. So I will go with this method. Looking at the signals, I will go with h of t convolved with x of t. That means I want this signal to be static and this should be the time shifting one. Okay, so let's from this h of t convolved with x of t, my y of t expression will be, so tau varying from minus infinity to plus infinity, h of tau and x of t minus tau d tau. So this is the expression from convolution integral. Now let's plot the signals x1 of tau, x of tau and x of t minus tau. So first I will plot h of tau. So this becomes 4 into e to the power of minus tau. The signal from here to here at any point, its value will be the same, 4 into e to the power of minus tau. Now coming to this signal, first I will plot x of tau. Signal varying from minus 2 to plus 2 with amplitude 1 here. Okay. Now let's take x of t minus tau, that is with the t is equal to 0. Considering t is equal to 0, since we both are having the same limit, plus 2 will become minus 2, minus 2 will become plus 2. So this is the origin, and minus 1 plus 1. So this is tau, amplitude is 1. But since it is t minus tau, here tau will be equal to t minus 2, and here tau will be equal to t plus 2. Now if you are having difficulty finding this, you have a simple procedure to go through. I will explain here. Just define the signals as it is in their respective terms. First you start with x1 of tau. Now if you see x1 of tau is equal to 1, x1 of tau is equal to 1 from where to where? For t less than or equal to plus 2, greater than or equal to minus 2, and it is 0 for others. Okay, so this is x of tau. Now if you want to define this, so this is x of t minus tau. Now x of t minus tau is also 1, but here comes the limit. Now this one, if you observe, here it is tau. I think I should have mentioned tau here. Okay. So tau, in place of tau, here it is t minus tau. T minus tau less than or equal to 2, greater than or equal to minus 2, and it is 0 for others. Now if you take this, if you simplify this, it is minus 2 less than equal to t minus tau less than equal to plus 2. We want tau here, keeping only tau, move this here. So that means this will become minus t and here 2 minus t, multiply by minus. So then what happens to this one? 2 plus t, this will become greater than or equal to, and this becomes plus t minus 2. That means for tau between t plus 2 to t minus 2, so this, in other words, you can write it like this: t minus 2, t plus 2. Okay. So then you can see the limit, x of t minus tau, I have written this is 1 for tau varying from t minus 2 to t plus 2. So this is t minus 2 and this is t plus 2. Okay. So this end will be t minus 2 and this end will be t plus 2. In this way you can get the limit here, and don't get surprised. That means we have taken the reversal of this, and then we have to find out from where to where it exists. So whichever comes to this one, so t minus 2 will be the negative index and t plus 2 will be the positive index. So this is how you get your limit here. So this is the way you can find out the limit if you are having any trouble. Or in the previous videos, I have told you why this point will become t minus 2 and how this one will be t plus 2. You can refer those videos, okay, while explaining in convolution sum. So let's continue with the problem here. Okay, let's start performing the convolution. Now the static signal is h of tau, which is varying from 0 to 1. So this is my h of tau. Now come to this signal, the shifting one. I will take this as case 1. Now observe this, the signal is varying from t minus 2 to t plus 2. Now I want to keep this t plus 2, that is the first case where there is no overlapping. And here you can see this at 0 the amplitude of the signal is 4 and it is gradually decreasing with respect to time. Now here the amplitude of these two signals is 1. So here it is, the signal, and the signal is having a duration of 4 divisions. So t minus 2 and this one is t plus 2. Here it is t plus 2 and this is the origin, amplitude 1. So this is my x of t minus tau. As you can see, there is no overlapping here. The signal are not getting multiplied. So that means for t plus 2 less than 0 or t less than minus 2, there is no overlapping. Therefore, h of tau into x of t minus tau, the multi-product of these two will be 0. Therefore, y of t is equal to 0. In the next case, I will move this t plus 2 here and let's see what happens to the signal. Next case, case 2. So h of tau and I want to keep the amplitude as 1 and it is the signal which is varying from t minus 2 to t plus 2. So this is x of t minus tau with amplitude 1. I can see this part. This is the overlapping region. Okay, so you should consider this as well. This part is overlapping. Now from where it is overlapping? From 0 to t plus 2, the signal is overlapping. Now how do you define this case? So t plus 2 less than 1 greater than 0. So that gives you t varying between -2 to -1. For this particular region, what happens to y of t? Let's find out. Y of t is equal to integral of the overlapping region is between 0 to t plus 2 h of tau x of t minus tau d tau. Okay. Now, in this particular duration, what is the value of h of tau? So, h of tau value is 4 into e to the power of minus tau. And what is the value of x of t minus tau? It is 1. So, that gives you integral of 0 to t plus 2 4 e to the power of minus tau into 1 d tau. Now, if you integrate this and if you apply the limit, you should get 4 into 1 minus e to the power of minus of t plus 2, something like this. Okay. Next, move on. We move to the next case. I have written the final answer here. Case 3. Now here in this case, I will move the signal further. I will take this outside the index 1 and let's see from where to where the signal will overlap. So this is h of tau and let's take the shifting signal. Now I am moving this here. This is my t plus 2. So it is 4 divisions 1, 2, 3, 4. So 0, 1 and here the signal is x of t minus tau with amplitude 1 and this is the overlapping region. So how do you define the case? You can see this. I have placed this in between 1 and 2. So t plus 2 is less than 2 greater than 1. If you simplify this, minus 1 to 0. Now the overlapping region is 0 to 1. So this complete part is overlapped. So y of t is equal to integral of 0 to 1 h of tau x of t minus tau d tau. Okay. So this is the part where the signal is getting overlapped. And if we substitute this 4 into e power minus tau into 1 d tau. Now if you integrate and apply the limit, so you will get 4 into 1 minus e to the power of minus 1. You can substitute further and you should get something like 2.5285. Okay, I have written the direct answer here just to save some time here. So this is from 0 to 1 over 4 1 into e to the power of minus 1. You can keep this as answer or you can simplify this by finding the value of e to the power of minus 1 and just multiply with 4 1 minus this value multiplied by 4 you will get 2.5285. So this is the next case and go to case 4. So here I will just extend this a little bit. Zero to 1. So 2, 3, 4, 5. So let's see what happens to this case. Now the shifting signal I will put here. So 1, 2, 3, 4. So amplitude is 1. This is my x of t minus tau and this is 4 into e power minus tau having amplitude 1. So again the overlapping region is from 0 to 1 itself. Now how to define this case for this one is t minus 2, this one is t plus 2, this end. So for t plus 2 less than 3 greater than 2, if you simplify this, you will get the region between 0 to 1. And since y of t is having the same overlapping region between 0 and 1, so if you perform integration of these two products, so you will end up with again 2.5285. Okay, so let's move to the next case. I'm just taking the next one, case I think 4, I mean 5, case 5. So here we'll further move the signal to the right. Four into e power minus tau. This is 0 to 1 here. So 2, 3, 4, 5. So let's take now observe. I will keep this t plus 2 here. So 1, 2, 3, 4. So 4 divisions. It is having 4 divisions. Now, so I will be keeping this t plus 2 here. So this is t plus 2. Now this signal is having 4 divisions. So 1, 2, 3, 4. So this will be my t minus 2. Okay. And again the overlapping region is between 0 and 1 here. Now how do you define the case here? For t plus 2 less than 4 greater than 3, simplify this, you will get 4 minus 2 as 2 and 3 minus 2 as 1. For this duration, again y of t is having the same region as the overlapping one. So the product of these two, when gets integrated, you will get the same answer as before, that is 2.5285. Okay. So next, case 6 here. So let's plot the signals. So 0 to 1 is my h of tau, 4 into e power minus tau. So 2, 3, 4, 5, 6. Now in this case, I will keep this t plus 2 between 4 and 5. Let's see what happens. So here is the signal t plus 2. Now 4 divisions, 1, 2, 3, 4 here. So this is my x of t minus tau with amplitude 1. I think I forgot to write here. Amplitude 1. Now this point is my t minus 2. So we got a new limit, the overlapping region, that is from t minus 2 to 1. So how do you define this condition for t plus 2 less than 5 greater than 4? So simplify this. So you'll get 2 to 3. So what is y of t in this particular duration? Y of t is equal to integral of, now the overlapping region is from t minus 2 to 1. Let's see what happens to the signal. X of t minus tau d tau. So if you integrate this, you should get and apply the limit 4 into e to the power of minus t minus 2 minus e to the power of 1. Now you can further simplify, but you have to apply values of t to get the final answer. I can keep it here, simplified to this value. So this is what you are going to get after simplifying and applying the limit, after integrating and applying the limit. Let's move to the next case. I think this will be the last one, case 7. So here I think the complete signal will move out with no overlapping, but we have to show that. So 0, 1, so 2, 3, 4, 5, 6, 7, 8, 9. So just elaborate this. 4 into e power minus tau with 4 here. Now let's write the overlapping signal. As you can see, in the next case I will be placing between 5 and 6. T plus 2 will be placed between 5 and 6, that is here t plus 2, and 1, 2, 3, 4, 4 divisions. So this is my x of t minus tau with amplitude 1, and this end is t minus 2. Now the signal, you can see there is no overlapping, and that means y of t will be 0. So we have shifted the signal from one end to another end of h of tau. In the first case we started with no overlapping region, and then we got some of the region which overlapped on h of tau and x of t minus tau. They both get overlapped, and finally we arrived at a point where there is no overlapping happening. So from this point onwards, y of t will be 0. So for t plus 2 less than 6 greater than 5, or if you simplify this, t between 3 and 4 for this particular region, or you can simply write it as for t greater than 3 to keep it simplicity, because t is greater than 3 less than 4, and from this onwards it will be 0 here. So there is no overlapping. So therefore h of tau x of t minus tau, the product will be 0. That means y of t is also 0. Okay. Now we can summarize this y of t with all the conditions here, which we have derived in the first case, from case 1 to case 7, I guess. Now in the first case, for t less than minus 2, our y of t is 0. So let's take this one. For t less than minus 2, y of t is 0. So that's the first case, t less than minus 2. Next, now in the second case, for t between minus 2 and minus 1, it is 4 into 1 minus e to the power of minus t plus 2. So that is the value for y of t, 4 into 1 minus e to the power of minus of t plus 2 for t varying between minus 2 and minus 1. Next case, in case 3, from minus 1 to 0, y of t is 2.5285. I think this repeated for several times. For between 0 and 1 also it is 2.5285, and between 1 and 2 it is 2.5285, and till case 6 we got the same answer. So that means from minus 1 here, from minus 1 to plus 2, we have 2.5285 as the value for y of t. 2.5285 from where to where? For t varying from minus 1 to plus 2. And from 2 to 3, we have 4 e to the power of minus t minus 2 minus of e to the power of minus 1. So this is the value of y of t in this particular duration. So let's write it here. 4 into e to the power of minus t minus 2 minus e to the power of minus 1. So this is for value of t greater than or equal to 2 less than 3. And finally, y of t will become for values of t greater than 3. Okay. So this is the final answer for y of t. We have summarized for all the limits. Hope you have understood this problem, and I will ask you to plot y of t by using these values. So here you have to put values for t from minus 2 to minus 1. You will get the value for that one, and using that you can complete the plot. And here it is 2.5285 from minus 1 to plus 2, so that is okay. And from 2 to 3 you will get and again an exponential signal, I guess. I will just plot it, and I just want you to mention, I will just give you the plot here, how it will look like. I want you to make sure whether you are getting the same or not. So this is the plot of y of t. So for t less than minus 2, y of t is 0. So that means here it is 0, and for t greater than 3, then also it is 0. So the signal exists between minus 2 and plus 3. From minus 2 to minus 1, we have e to the power of t plus 2. I think I forgot this bracket here mentioning t plus 2. So put the values for t, and from minus 1 to plus 2 we have a constant value here, that is 2.5285, and from 2 to 3 we have to substitute the value here. So you should get an exponential signal here and a decreasing exponential here. Okay, so these two. Okay, so just apply minus 2 and minus 1 for this value, for this expression. You will get the value for that, and here you have to apply plus 2 and plus 3. You will get the answer for this one. Simply saying, if you apply plus 2, this becomes e to the power of 0, that is 1 minus e to the power of minus 1. Again you will get 2.5285. And if you put 3 here, 3 minus 2 is 1, e to the power of minus 1 minus e to the power of minus 1, both will get cancelled. You will get 4 into 0, so it will come to 0 here. Come to this expression. If you put minus 2 here, minus 2, e to the power of minus 2 plus 2. So minus 2 plus 2 is 0, so that becomes this as e to the power of 0. E to the power of 0 is 1, 1 minus 1 is 0. So that's why at minus 2 you will get 0 here. Coming to this minus 1, if you put minus 1, e to the power of minus 1 plus 2, you will end up with 1 minus e to the power of minus 1, which is the same in this case. 4 into 1 minus e inverse. Again you will end up with 2.5285. So it is not that difficult. Looking at the expression, you don't feel that it's difficult to get the answer. Just apply the values as shown in the previous problem. You will get the answer and you can complete the plot. Anyhow, I have written the plot here, but I want you to confirm whether you will get the same or not. Okay. Anyhow, this completes the problem here. And in the next we'll move to the properties of LTI system, okay, in the next video. And I think I have covered different types of examples by taking different kind of signals in convolution integral. So in the next video, we'll move to the properties of convolution, uh, not properties of LTI system, not convolution integral. Hope you have understood the problem this, and if you have any kind of queries, do reply or comment, and thank you for your time.